Everyone, thank you for coming to part two of our driver webinar series. If you attended our previous one, I'm Sam Cantor, the section head of economic geology at Minerva Intelligence. And today we have our CTO and co-founder, Clinton Smythe, who will be giving the cognitive AI half of our two-part driver series. So thank you, Clinton. And when you're ready, please take it away.
Thanks very much, Sam, and good day to everyone attending the webinar. It's a pleasure for me to present this work that's the culmination of many years of geochemical thinking. So we will start by going to the next slide. So Minerva Intelligence, by brief review, is a Vancouver-based software company specializing in applying knowledge engineering and cognitive AI to geoscience. And today we'll be talking, as Sam said, about the second component of Driver, which is one of a suite of products in our economic geology department. By way of a table of contents of things we'll cover today, we'll have a short, the 2-minute video that some of you may have seen that summarizes the machine learning component, the first component of Driver, and sets the stage for us to talk more about the cognitive side of things. We'll have a brief one slide presenting how Driver fits in Minerva's e-science paradigm, and then we'll look at the actionable outputs that Driver produces and touch on how it explains itself and can give advice to people using the system. And then the bulk of the presentation, which is quite heavy going for someone who's just interested in finding their new ore deposit, is how Driver achieves the interoperability between the data that comes out of your laboratory and your logging of core, interoperability between that data and all the knowledge that is tied up in many scientific publications and the heads of a lot of very knowledgeable geologists. And that involves semantic networks, linked data, terminological standards, taxonomies, ontologies, and then applications we've written to support those. And all of that architecture in a software context is built in a framework originally envisioned by Tim Berners-Lee for the internet. It's called the semantic web, and we'll close off with where our software fits in that paradigm. So to begin with, we'll play a 2.5-minute video as a refresher on what Driver does.
In order to find mineral deposits, companies spend millions of dollars collecting drilling data. They then analyze the chemistry of their drilling samples for 30 to 40 elements. But because of time and budget constraints, they typically only focus on a few of the elements analyzed. Mineral deposits are complex, but they have multi-element geochemical signatures that can be used to enhance deposit understanding. These geochemical signatures are useful for exploration, mining and metallurgy, and environmental applications. But modeling these multi-element geochemical signatures is costly and time-consuming, and it's impossible for humans to model everything. Driver by Minerva Intelligence was built to solve this problem. Driver uses massive cloud computing power combined with cutting-edge artificial intelligence to quickly and accurately model mineral deposit geochemistry in 3D. Unlike other software, Driver uses exhaustive modeling to create tens of thousands of block models of every element in the dataset. Driver then uses artificial intelligence to test every model and automatically find the chemically enhanced zones that most closely represent reality. Driver also calculates how every possible combination of elements spatially overlap, allowing to reveal the true geochemical complexity in your deposit. The Driver results integrate Minerva's intelligent cognitive reasoning software to identify meaningful comparisons between your deposit and others from around the world. The Driver system can be accessed online from anywhere in the world. It interacts seamlessly with existing geological modeling software and harnesses enough computational power to process even the largest geochemical datasets in less than a day. Driver helps you to discover geochemical features and patterns in your deposit using only data you've already paid to collect. For more information on Driver or to try it out for yourself, please visit our website at minervaintelligence.com/driver.
So that's the background. That's the machine learning part of driver, which is shown in this diagram as ML with the red brackets around it. This slide then presents the paradigm within which Minerva's been developing software for the last good few years. And what it really shows is that data comes into the system. We may use machine learning to extract features from it and align those features and how they're described to an international terminology standard, where we at the same time have knowledge coming in from documents and experts via our knowledge capture system. We can reason about what comes out of your drilling data because it's all in the same terminology as the knowledge we've captured, and from that we can produce actionable results from you. This paradigm is described in a 2009 paper by David Poole, who's a co-founder of Minerva, professor of artificial intelligence at the University of British Columbia, on this reference. What we're going to show today is how the driver components actually fit into this paradigm, and we'll talk about each one of them. This paradigm applies to landslides, could apply to medicine, could apply to any scientific endeavor. So during this presentation, we'll be showing how your drilling data comes in there, aligned to terminology standards, uses knowledge from USGS geoscience or individual scientists, and comes out here. So the machine learning element of driver typically produces DXF files that delimit zones of enhanced mineralization within the center of the deposit or exploration target that you're drilling. In this case, this is a tin deposit, the Ashmash deposit in Morocco. Tin is shown here, and then other elements, silver, overlap between tin and silver, sulfur zone, potassium zone, overlap between silver, tin, beryllium, and bismuth. All of these zones are the kind of things that we reason about in the cognitive area. So we're not reasoning in a vacuum. A lot of people have been working on bulk geochemical zonation of different kinds of mineral deposits. It's a difficult job to work on because you really need lots of data, and the tools for evaluating all that data haven't really been around for a long time, and neither has the computational power. People like Scott Halley have documented the elemental distribution bulk geochemistry zonation we'd expect around porphyry copper deposits, probably one of the more advanced deposit types understood with respect to element zonation. And this is an extract from his 2015 paper where he actually lays down on paper the parts per million levels we'd expect at different parts in and around a porphyry copper deposit. Not only does he delimit those, but he also talks about the sequences in which you could expect these elements to be zoned as you move away or towards the deposit. And very often these zones of enhancement are overlapping, and sometimes some elements are present and some are not. So the evaluation of these overlap zones is as important as evaluating individual elements, and is very complex when we consider the number of elements and permutations and combinations that can exist. So we actually need a computational platform in which to manage this complexity, and Minerva's had that for many years in an ontology for describing mineral deposits, specifically in terms of the zones within the ore zone and the zones outside of the ore zone. And there isn't time in this presentation to discuss the great details of those, other than to show in this schematic diagram of a typical ore body where the boundary to economic mineralization is the darker black line around the circle here. The zones inside are different mineral or elemental combinations, different mineralization assemblages, and as soon as particular alteration assemblages are recognized outside the borders of economic mineralization, we call them alteration, and there are many ways those zones can overlap each other or different host rocks. So all of this has to be handled within a cognitive reasoning environment. The cognitive reasoning environment on Minerva's platform takes place within the Solus software, and Solus does a number of other things for users. One of the most important things it does is align whatever terminology is coming in from the client working area to international standards of terminology. because those are absolutely essential for interoperability, and it is those standards of terminology that we use when we capture knowledge from any scientific papers or from any geological surveys. Before we sign into Solus, I just need to review what is actually coming out of Driver. So a couple of slides before, we saw that the machine learning side of Driver produces elemental zones of enhancement. Within the Driver ML using interface, one is able to select the different elements, we'll talk about that in a moment, which constitute the elements of interest in the ore body being evaluated. But one is also able to specify the rock types hosting the mineralization, and very importantly, the rock types that are not present, because when reasoning with the international literature, it's sometimes as important to say what your mineralization is not hosted in as it is to say what it is hosted in order to focus in on other deposits in the world that are like yours. So within this environment, before moving into Solus, here the geologist has said his host rocks in this particular case are samites, peelites, sandstone, and schist, definitely not hosted in ultramafic and gabbro. Now, this information, along with the information describing these zones, is passed into Solus, and before it gets passed into the reasoner, the terminology is aligned, and you'll see that GeoSciML, the international standard we use, does not have a term for samite. So what Solus makes it easy for the geologist to do is map samite to metamorphic rock, and that's the term that will be used in subsequent reasoning about the outputs from the machine learning. So here we have a semantic network, which is how we represent knowledge in Driver. We'll come back to those structures in a moment. But still within the Driver machine learning environment, we see that the geochemical zones and the zone overlaps can be evaluated under different profiles. So we've already mentioned that Scott Halley has been very specific about what suites of elements and what concentrations one can expect in looking for a porphyry copper deposit. And because when you've got 40 elements and a great many combinations of overlaps between those, it's very helpful to limit the elements that you look at to certain profiles. So in this case, within the Driver interface, we are specifying the elements of interest to us, and we're specifying that we're using Scott Halley's recommended thresholds above which one would expect elements to be considered to be enhanced. So this allows us to filter out a lot of enhanced areas that may not be important in a porphyry environment. So what I would like to point out in this bottom left-hand corner here is that what Driver is also allowing you to do, it's telling you when particular elements that you've selected have not overlapped at all with each other, and those are highlighted in red. The ones that do have overlaps are highlighted in black, and the actual volumes in terms of millions of cubic meters is specified here. So we can see that in this particular deposit, which is a porphyry deposit in the Star Mountains of Papua New Guinea, in the drilling environment being evaluated here, we have 3.2 million cubic meters of enhanced silver and copper overlapping each other, whereas as soon as you look at the environment where tellurium is also overlapping with silver and bismuth, we're down to only 1 million cubic meters. So there's lots of detail there that we won't go into right now. But once that information is passed through into the cognitive and reasoning environment, Minerva's reasoning engine is then able to compare those outputs to any number of knowledge bases that we have. And on this screen, we're just showing the outputs from the Ashmash tin deposit being compared to 92 USGS deposit models. And here is the similarity ranking on the right-hand side, and the scores in the middle. By clicking on the match details here, the Solus environment will give the user an explanation for why the Ashmash underground hard rock deposit is similar to an alluvial placid tin deposit, tin skarn deposits, and so on. Not only are you able to compare the outputs from Driver with conceptual deposit models, you're able to compare your outputs with actual mineral deposits or mineral occurrences throughout the world. We have a growing knowledge base of such deposits and mineral occurrences. In this case, we're comparing our outputs on the Ashmash deposit with 1,000 mines in Australia, also ranked on similarity. So An example of the explanations that are given in the Solus environment is shown on the left. So if I go back, if we click on a match details, any one of these clicks will explain why Ashmash is similar to whatever deposit we're looking at. And the explanation report is something like this, where matching characteristics are highlighted in green and conflicting attributes will be highlighted in red. Within the reasoning engine, the software is able to recognize when a particular rock is a kind of some other rock. So in this case, it has recognized that a quartzite is a certain kind of a metamorphic rock, which a standard SQL query in a relational database would not have done. In the environment, the operating environment as well, instead of clicking on the match report, within the match report, one's able to click on advice, and the system will tell the user what additional information will either improve or degrade the ranking or the score, and the user can take that advice by adding that information and hence zeroing in on just the deposits that are similar to theirs. Enhancing, in other words, this information with information that may not come from driver, for example, tectonic setting, age of the deposit, and information such as that. So this brings us on to the fact that deposit models and driver output descriptions can be edited in Minerva's knowledge editor based on the advice given by the system, interest in a new deposit model, or additional non-geochemical data available about the mine or exploration target under evaluation. That happens in our knowledge capture environment with strictly controlled vocabulary. We have a new reasoning engine that hasn't been released yet, which incorporates Bayesian techniques for reasoning with conceptual models, such as mineral deposit models. The properties of those models are statistical in nature, always, sometimes, rarely, never, and their weights when evaluating similarity rankings take into account prior probabilities. This determines how diagnostic a property is of a model. We will be providing workshops in the future on how this Bayesian reasoning works, and in particular expanding on the important knowledge area of prior probabilities. So what we're really talking about when we talk about prior probabilities is how rare or how likely is it to find a gold anomaly compared to finding a silica anomaly? How common is granodiorite compared to kimberlite? These are poorly measured variables in the world of geochemistry today, but there are knowledge bases that allow us to approximate them, and we believe that with ongoing work like this, we'll be firming up on those kind of very important global variables. More on that in another workshop. So not only can users of driver expand on what the outputs from their machine learning are, but they can create and maintain their proprietary knowledge bases of deposit models or mine target descriptions, which will be interoperable both with what comes out of their drilling results and the substantial knowledge base already created by Minerva. So here's an example of someone putting in a revised tin model, a sort of update on the USGS model for tin scars. So here's a quick video just showing the extent of our knowledge base. We'll just look at the world, and I shall pause it now to mention that any points that are in red are representing mineral deposit descriptions in the world that we have more than 25 attributes for. So that's a rich description, lots of knowledge about that deposit. The ones in blue are something between 10 and 24 attributes, and the ones in yellow are generally mineral occurrences that we have imbibed using Solus from larger databases where we've mapped the terminology from each geological survey or data source's unique terminology to the internationally standard terminology. So we have what we call scant quality descriptions there, but these are very useful for target generation. So as you'll notice when we zoom into North America here, we have all the mineral occurrences of British Columbia and New Brunswick in the system, which gives us thousands of mineral occurrences to compare against either our drilling results or the deposit models that we want to look for. For example, critical metals are the flavor of the month at the moment, so one could create one's own lithium model and search the mineral occurrences of British Columbia using our software. So as we zoom in, you will see the richness of our global coverage. one. We zoom right in now. What we're dealing with, these are individual mineral occurrences in British Columbia. So our ontologically controlled deposit and occurrences knowledge base is what I've just been showing you. These are used to enhance the interpretation of complex lithogeochemical zones. And this slide describes the deposit models and the fact that the ones we have come in from Geoscience Australia, British Columbia Geological Survey, Geoscience here, and the USGS. So now a quick recap of what the actual value propositions are coming out of Driver. Now, not only can you see where the zones are in your drilling or in your mine, what can you do with that data either before you've compared it to an international knowledge base or after you've done that. And the value proposition is fourfold, really. It enhances your ability to interpret the data for exploration. I won't go into the details of this slide other than to say this is zonation around porphyries, this is zonation documented around VMS deposits, and this is zonation documented around iron oxide copper gold deposits. The zonation is potentially critical for geometallurgical studies and geometallurgic domaining. For anyone who's going to mine, it provides critical input to environmental protection and ESG behavior by companies, because Driver produces the concentrations, the average concentrations for the enhanced zones identified, and these are then easily indexed against the rich environmental geochemical models that have been published by the USGS, the tolerated runoff compositions from waste dumps into streams and into soils from either waste dumps or tailings dams. So very important background information there. And potentially even when there is a proxy relationship between a geochemical element or a zone and rock strength, then sometimes we find that the Driver outputs can be quite important in terms of, can assist with mine planning as well. So now on to what is required on the computer side to achieve this knowledge interoperability. It's really achieved by converting the information that typically used to be in relational databases and is difficult to query from a cardinality, how many values something can have, and also the classification relationships where your querying or comparison algorithms need to know that a granite is an igneous rock and that a sandstone is a sediment. All of that is much easier to do in the environment of linked data and semantic networks. There's been a blossoming of this kind of technology in the last 15 years, and people often use the word semantic network and knowledge graph interchangeably, and it's worth saying now that we store our information in semantic networks, which are a kind of knowledge graph, but each semantic network has at its head a particular concept, like a mine or a person or a disease or a mineral. Whereas a knowledge graph, which we see on the right, is a very open collection of linked data. So in a semantic network, data is linked using the same technology as is used in knowledge graphs, but it's linked to descriptions of specific things that one reasons about. Whereas in a knowledge graph, there is effectively no end to those links, and they are cyclical. So you can extract semantic networks from knowledge graphs, but they are different. So the fact is that very large volumes of human learning are available for expression on computers and use in problem solving in cognitive AI. This human knowledge spans a range of different things. The knowledge is in scientific literature. It's in knowledge summaries, which might be drawn graphically, as we'll see in a moment, from those scientific literatures. But that knowledge is also embedded in taxonomies and ontologies, which are kind of implicit in our brains, but need to be made explicit on the computer. The framework within which all this kind of knowledge is most easily represented in today's technology is in semantic networks. So what we see here are 4 different semantic networks, each describing a different mineral deposit. Each of these is interoperable with the other. So what's the background then to getting this technology to work? Well, formal knowledge structures and workflows are needed, and these are built with terminology standards and ontologies. Now, an ontology, if we look at the bottom left-hand corner here, really represents the meaning of symbols, such as words. So we use an ontology a bit like a grammar to relate the concepts like minerals and elements and tectonic settings and geological time all together. Those different concepts all have their own terminologies. And in order to do that for a practical work environment, one actually needs to sketch out the kind of thing you want to describe. And here is a cartoon that pretty well describes just about any kind of mineral deposit in terms of a boundary to the mineralization, the dark red line, the mineralization in the middle, different assemblages that may straddle the boundary of the mineralization to go outside of it, in which case we call it alteration, and the mineralization and alteration may be hosted in different rocks. These are subjects that are discussed in all scientific papers about mineral deposits, but not always expressed as explicitly as this. So when wanting to extract that knowledge and putting it into a computer system, you actually almost have to convert your thinking to this, and sometimes a form like the one on the right is helpful to do that, where you identify what the mineralization assemblages are, what the alteration assemblages are, which zones they're in, which host rocks the zones are in, and whether there are country rocks around it which don't even have alteration or mineralization in them. You know, these overlaps end up resulting in quite a large number of unique, what we'd call overlap zones. And this is the complexity that we're managing when we manage the outputs from the machine learning on driver. So Minerva's been doing this for many years, and as a result, we have a great many both mineral deposit models and instances of mineral deposits described in the literature, transformed using this template onto a worksheet like this, and then through our knowledge capture interface expressed as a semantic network like this. So here's a diagram of the deposit model, the deposit in this case, which adheres to the principles laid out in this template. And these are actually the number of different alteration assemblages. There are only 2 mineralization assemblages. They result in 6 different zones, and these are the rock types that the zones are hosted in. So here are just a few of the many worksheets like this that have led to the knowledge base of our richer descriptions. I need to remind you that we are also able to mass import from suitable quality databases thousands of descriptions of mineral occurrences or mines if the richness of those relational databases is adequate for mapping to the international standard terminology. So the terminology standards for interoperability are absolutely critical. And where do we get those? Well, we've for years been getting them from the emerging and always constantly being upgraded international terminology standards. We standardize on GeoSciML. If you want to look up where that comes from, just Google GeoSciML space taxonomy or GeoSciML ontology or GeoSciML geology, and you'll be taken to a great number of vocabularies. The next committee meeting on GeoSciML standards is scheduled for the next within the next 2 weeks. So these are very live and living standards. Most interestingly, China's Geological Survey has entered this domain and is contributing a lot in English. So this DDE standards task group is primarily financed by the Chinese, and although a lot of the expertise is going into it from other geological surveys, so Mark Rattenbury, who's in charge of their standard terminologies, is actually from the New Zealand Geological Survey. If you want to find out what's going on in that environment, just look up Deep Time to Digital Earth. So these terminologies generally form part of taxonomies, and many of the taxonomies, even some of the standard international ones, are not pure taxonomies. They are mixtures of what we call taxonomies and partonomies. And it's very important in a knowledge engineering environment, in a sort of a reasoning environment, to distinguish the two for the following reason. In a taxonomy, which is a hierarchical relationship between classes, properties in a higher class propagate down the tree towards things in a more specific class. So in this taxonomy of rocks, we go from rock igneous to rock igneous plutonic, plutonic to gabbro. And so when we're reasoning about gabbros, anything that we know about igneous rocks, any properties of igneous rocks are true of gabbros. So properties propagate down a taxonomy tree like this. Whereas in a partonomy tree, the propagation of attributes is in completely the opposite direction. So a rock has a part of a rock which is a mineral, and a mineral has a part which is an element. So not everything about an element is true of the mineral, but some of the things about a rock that has a mineral are true. So, for example, element number 1 may have an electron in K2 orbit. That is not true of the mineral because the mineral doesn't have electrons in particular orbits. That's a specific property of an element. But if a mineral has arsenic, then the rock has arsenic. So some properties propagate up a tree like this. And this is the kind of thing that is managed in the ontology, at the ontological level. But if a taxonomy is incorrectly put together, and if it mixes up this kind of hierarchy with this kind of hierarchy, it cannot be used in an intelligent application in a cognitive reasoning sense. So Minerva has developed over the years an application called ACE, which stands for Aristotelian Class Editor. And we use ACE to purify, if you like, all the taxonomies we used before we use them so that our reasoning is 100% correct. So what you see in this diagram is a little bit about how ACE works. ACE really works on the principle that any concept you want in the taxonomy must have a number of properties. And from those properties, we can use a logic inference engine to infer the hierarchy of that taxonomy so long as we've defined all the characteristics. And in this case, you'll see the geoCyML rock types listed on the left here, and what we've made explicit in all sorts of columns on the right are the properties of these rock types. And once we have those, we can infer the taxonomic hierarchy for the rock types. Interesting, it's not as simple as you may think, because the properties of rock types themselves may be hierarchical. So in the case here of the grain size of a rock, you can see that grain size is itself hierarchical. So this hierarchy has to be taken into account when inferring the hierarchy of the rock taxonomy. Our ACE application does all of that. So what this screen shows is the representation of the collection of rock type concepts on this left screen in its asserted form. And if within ACE you click on infer, ACE will go and infer this hierarchy, which you see here, where we start at the top with rock. We go down to the next level, igneous rock, basic igneous rock, gabbroic rock, and finally a gabbro. So this hierarchy has been inferred by ACE from all of these properties of all of these different concepts of rocks. As I've mentioned before, we use an ontology editor together all these different taxonomies to describe the top-level concept that we're interested in a semantic network. So Minerva's precursor used to have its own ontology editor, but that has been supplanted by developments in the international knowledge engineering world. There are a number of powerful ontology editors on the market these days. We use the ontology editor within EDGE, the Enterprise Data Governance application of top grade. And what you see here is a snapshot of our ontology. By clicking on the deposit, the ontology editor shows us all the properties and relationships that are important for describing something such as a deposit. So the knowledge is captured from the literature into the computer under ontological control. So what you see in front of you now is a snapshot of our knowledge capture interface in Solus. And you can see that what the knowledge engineer is doing at the moment is entering a description of something called deposit Duluth Copper Nickel PGE version 2. It's a deposit model type. She's entering that the deposit has rock host, gabbro. They've opened the tree to actually see what rock types are permissible from the taxonomy that the ontology is using. And within this environment, the knowledge engineer is also provided with the definitions of those rock types, because if from the literature they see a word that is not in the approved vocabulary, they're going to have to find out what term most closely matches that. And so the definitions of those terms are really important. And then the engineer from the literature is meant to infer from the science writing whether the person describing this model says that this rock type is usually, sometimes, rarely, or never in the model. And the new information I was talking about needed for Bayesian reasoning is how common is that rock type, gabbro, in the world. So in this environment, this person is saying that gabbros are uncommon rock types. What this leads to is the fact that the rewards for this rock type being present is a very weak positive reward, and if the rock type can be asserted not to be present, it's a weak negative penalty during the reasoning. So again, we will be mounting a different webinar for those who are interested in the coming months on how this Bayesian reasoning works, and in particular how it benefits from background knowledge of how common elements or minerals or rocks are in the global environment, or in a particular contextual environment such as British Columbia, which would be different from Australia, of course. I mentioned before that large relational databases can be transformed into interoperable semantic networks. Minerva uses the proprietary Solus application to do this, and it's typically a two-stage operation. It involves terminology alignment and restructuring from tables to networks and graphs. So what we get within Solus to produce that large knowledge base that I showed you earlier, this all happens in Solus. Just need to say a word here that in the world of cognitive AI and the semantic web and false news and so on, those who read about this will find that there is something called the semantic stack, which is the architecture of the semantic web as envisioned by Berners-Lee, and it starts really at the bottom with the web platform and moves up through syntax, knowledge representation, the semantics that I've been talking about, rules of reasoning, all of which are just explained in logic. But at the very highest level is the question of trust. So how do you get someone to trust the knowledge that you're now serving up on the internet or serving up in a proprietary application? And the way Minerva goes about generating trust, making sure that all the knowledge that it's reasoning with when it's giving explanations or advice is indexed back into the scientific literature from which the knowledge came in the first place. And in order to do that, we developed a document management system called Leo. There are many document management systems out in the world, but one of the very special things about Leo is that it makes it easy, particularly easy for the user to search those documents for the internationally approved standard terminology. So access to the taxonomies is provided within Leo, and I may get a chance to show that today. But what we're showing in the user interface of Leo here, we're not searching actually for any of the standard terminology. We're just searching for the name Cadia, which is the name of a particular mine. You can see, maybe just be able to see on the screen here, that we're searching in our exploration library. So one could search across the 4 different libraries that we have supporting Driver, one for exploration, one for metallurgy, one for environment, and one for mining-related geochemistry. But in this case, we're searching the exploration scientific library for Cadia, and you can see that we have at least 4 or 5 papers in the library there describing Cadia, or mentioning Cadia at least. It would actually be an interesting exercise, which we haven't done yet. We have one description of Cadia in the system, but to get 5 different geologists to extract the knowledge as described in the 5 different papers on Cadia, and then compare all of those together using Minerva's reasoning system. And what I'm talking about now is actually research. By making information interoperable like this, we believe that Minerva's technology, be it at the semantic level or the description of mineral deposits or deposit models, is going to be an essential tool in the future for understanding mineral deposits and generating new knowledge. So along these lines, for the last couple of years, Minerva's been developing a new mineral deposit classification system in ACE. So what you see down the left-hand side of ACE, these are all the concepts, deposit types, deposit models that we're developing. Across the top here are all the attributes of those deposit models. The work that's ongoing on this classification has been submitted actually as an abstract. It hasn't been accepted yet for the upcoming Society of Economic Geology meeting in Whistler later this year, and we hope it's going to be accepted. Nevertheless, the system is being led by Dave Lefebvre, who used to be the chief geologist of the British Columbia Geological Survey, who around 20 years ago was responsible for the publication of 110 mineral deposit profiles, models, if you like, of deposit types that are discoverable in British Columbia. So this slide kind of puts into context the history of deposit classification, and what we think is happening right now is a new discipline being applied to mineral deposit classification that recognizes perhaps a need for additional broader classes that sort of recognize the continuity between deposit types. The challenge is how to represent that, and one of the ways of representing that continuum is by explicitly representing the attributes in a taxonomy maintained by ACE. So we're getting close to the end now. Drivers is designed, as we've said, around scientific theories that make probabilistic predictions paradigm. What we've shown is how the different elements of knowledge coming into this area respect the general design paradigm we have within Minerva. And as a last slide, I want to show how these software components all map to the Berners-Lee semantic stack. So we're looking at an older version of the semantic stack now, which is just in 2 dimensions, not the 3 that I showed before. So Solus sits here at the data interchange level. Solus actually represents things as semantic networks. RDF is a semantic network framework. ACE plays its role at the taxonomy level. Our ontologies in top grade are expressed in OWL, and or there are other languages for expressing ontologies in today's world. And then our reasoner sits at the proof level here, and Leo feeds in right at the top at the trust level. Knowledge capture uses all these for putting in knowledge using controlled by OWL. I'm quite happy to just quickly show 1 or 2 live demonstrations of what happens. Go straight into the Solus situation. So here's an example of 3 different runs. So these are outputs from a copper porphyry that was evaluated in Papua New Guinea. And we have 3 different runs of the output. So the first output, in this case, here's the semantic network information in serial form, compared against 90 USGS deposit models. And you can see these drilling results rank in this order against these different deposit models. And you can see it, the geologist working on it considered it was a porphyry copper deposit. It has been matched as well against, not unsurprisingly, against the volcanic hosted copper arsenic antimony deposit, somewhat surprisingly against copper nickel. And so one can ask, well, why are we getting these explanations? Well, first we can look at the one that we expect it to be, and you can see there are not a lot of attributes, but only 3 attributes, just the fact that it's hosted in a monzonite and that copper and gold are enhanced in it. We want to see why it matched to a volcanic hosted copper deposit. So we see there are more elements that are matched, and in order to, if we look for the advice, if we want to make the match worse, the system here tells us what we should add, which would discriminate what we're looking at from which would make the match with volcanic hosted copper arsenic antimony deposits worse. So now at the flick of a button, one is able to then say, well, I want to have a look at this deposit ranked against 70 mineral deposits in Europe. And those who know European mineral deposits will not be surprised that Bor district, this district, Acerel, Rosia Puene, Apuseni district, all the porphyry deposit hosting areas in Europe are coming up. And let's just compare it to Apuseni, for example. Here's all the information about Apuseni, and here's the reasonably scant information we have at this point about our drilling project in Papua New Guinea. And the last one that we can compare it to is 1,000 mineral deposits in Australia. And not surprisingly, North Parkes and Cadia come up near the top. So that's a quick look into Driver there. Driver itself, looking at the results before they've been passed off to the reasoner, obviously all the outputs are exportable to DXF at the click of a button for immediate drag and drop into your deposit modeling system, but you can look at them within the web interface as well. So what we're looking at right here, that's the copper zone in this very limited drilling, exploration drilling in Papua New Guinea. And here what we're looking at is the overlap between silver, copper, and tellurium. And if we want to look at the silver zone, which is interesting because silver in this deposit turns out to be much broader spread than the copper, we can simply turn on the silver and see that there is much more silver aerially, not necessarily compositionally, than copper. So that's that environment. This is the knowledge capture environment where we can either be looking at our tree for host rocks or the Bayesian probability requirements. All of these are interrelated. This is the subject of our next webinar. And if one wants to look for other rock types, they're all here in the tree. Finally, a quick look at Leo. As I've said before, we can either look at our metallurgy, mining, or exploration environment, and the taxonomies that I was talking about were all in here. So if we want to look for arsenates, for example, this is where the arsenates are in our exploration environment. If we want to look for arsenates only in the environmental environment, there are no results found, so we'll just look for pyrite instead to show. Let's look rather for pyrite and chlorine. Okay, so USGS, the Blackbird copper cobalt deposit, USGS environmental model has got something to say about pyrite and chlorine. So that's just a quick look into the 4 different applications that are supporting drivers.
Yeah, and if anyone has any focused questions, feel free to email us. We're more than happy to kind of go into detail on any of these and answer any other questions you may have. So thank you everyone for attending, and thank you Clinton for presenting sort of the full spectrum of what underpins Minerva's technology.